Hey guys, and welcome back to my science studio. In today's lesson, we'll be continuing our discussion on types of chemical reactions. In the last video, we talked about combination and decomposition reactions, which are essentially opposites of each other. And if you haven't watched that lesson yet, I highly recommend checking it out before moving on. Today, we'll be focusing on combustion reactions. And one way I like to introduce combustions is with a real-life example most of us are familiar with, driving a car. When you put gasoline into your car, what are you actually adding? Well, gasoline or fuel is a mixture of hydrocarbons. And a hydrocarbon, as the name suggests, is a compound made up of hydrogen and carbon. So when you turn your car on, that fuel begins to burn in the presence of oxygen gas. And this burning process is a combustion reaction. And as the fuel combusts, it produces a couple products: carbon dioxide gas, water vapor, and energy, released as heat, and sometimes light. That's why you'll often see exhaust coming out of the back of a car. That exhaust contains carbon dioxide and water vapor. And this is something I really love about combustion reactions, because the reactants and the products are very predictable. You see, in a combustion reaction, you always start with some sort of hydrocarbon reacting with oxygen gas, and you always produce carbon dioxide and water. So even if your teacher asks you to predict the products, combustion reactions are actually very student-friendly. The only thing that changes from problem to problem is the specific hydrocarbon and the coefficients needed to balance the equation once you predict the products, which again will always be CO2 and H2O. So the overall pattern stays the same every time. So with that in mind, let's go ahead and work through our first combustion example together. All right, so the first problem says, write and balance the complete combustion reaction for each hydrocarbon below. And we'll start with methane. Now, methane has the formula CH4. In organic chemistry, we call CH4 methane, and it's the simplest hydrocarbon. If you ever want a full video on naming hydrocarbons, please don't hesitate and comment below. But odds are your teacher in high school will likely give you the formula for methane, which is CH4. But I digress. Now, what does a complete combustion mean? A complete combustion happens when there is a sufficient supply of oxygen gas. In other words, the hydrocarbon burns fully. So the first thing you want to do is write the skeleton equation. And in a combustion reaction, we always start with a hydrocarbon reacting with oxygen gas. So we go ahead and write on the reactant side the hydrocarbon, which is the methane or CH4 gas reacting with O2 gas. Oxygen gas is one of the 7 diatomic elements. Remember your mnemonic, have no fear of ice-cold beverages. So oxygen gas exists as O2, 2 atoms of oxygen bound to each other. That too is important because if it's not included, then your balancing afterward will be totally off. But anyways, now in a complete combustion, the products will always be CO2 gas or carbon dioxide gas and water vapor or H2O gas and energy. You can include energy if you want, but we won't balance energy necessarily, just the atoms here, to fulfill the law of conservation of mass. Now, step 2 is to balance using my combustion strategy. Now, in a previous video, I talked about a trick for balancing combustion reactions. My tip for you is balance your carbons first, then your hydrogens, and leave oxygen for last. Why? Because O2 is by itself, so we can easily adjust it at the end. Okay, now we're going to count our atoms. On the reactant side, we have 1 C, 4 H's, and 2 O's. And on the product side, we have 1 C, 2 H's, and 3 O's, 2 from the CO2 and 1 from the H2O. Now let's go ahead and balance. First, balance our carbons. Well, on the left we have 1, and on the right we have 1 carbon as well. So we're good on the carbons. They're balanced. Now let's look at the hydrogens. On the left we have 4 hydrogens, but on the right we have 2. So ask yourself, what number can I add as a coefficient in front of the H2O in order to have 4 hydrogens on both sides? Right, if we add a 2 in front of the H2O, that gives us 4. So now our hydrogens are balanced. So now we can look at the oxygens. Well, for oxygen, on the left we have 2, and on the right we have 2 from the CO2, and we have 2 from the H2O. So 2 plus 2, that gives us 4 oxygens on the right side. So in order to have 4 oxygens on the left side, we would have to add a coefficient 2 in front of the O2 in order to have 4 oxygens on the left and the right side. And taking a quick look at this, doing a final check, looks like we're balanced. Now I want you to try the next one on your own. Write and balance the complete combustion reaction for butane. Now, balancing this reaction can be a little tricky for some students, but it's okay. Go ahead, pause the video, try it, and when you're ready, press play, and we'll walk through the answer together step by step. And I'll show you a neat trick along the way. All right, now let's check the complete combustion of butane, which has the formula C4H10. We'll start by writing the skeleton equation. On the reactant side, we have C4H10 reacting with oxygen gas to produce carbon dioxide or CO2 gas and H2O gas. Now we got to balance. First, let's count our atoms. So on the left side, we have 4 C's, 10 H's, and 2 O's. On the right side, we have 1 C, 2 H's, and 3 O's. Let's first balance our carbons. Well, we have 4 on the left and only 1 on the right. So if we add a coefficient of 4 in front of the CO2, that makes 4 carbons on the right and left sides. We have 10 hydrogens on the left, but only 2 on the right. So we add a 5 in front of the H2O. 5 times 2 gives us 10 hydrogens. So now we're balanced with the left side. We have 10 on each side for hydrogen. Leaving oxygen for last, we have to count on the right side how many we're working with. So we have 5 oxygens from the H2O, and we have 4 times 2 from the CO2, which is 8. 8 plus 5 gives us 13 oxygens in total. Now here's where students often get stuck, because oxygen comes in pairs as O2, right? It's a diatomic element. So what do? Well, hear me out. We can temporarily allow a fraction. To get 13 oxygens on the left side, we can write 13 over 2 in front of the O2. Yes, it looks super strange, but don't worry, we're fixing it next. To get rid of a fraction, we can multiply the 13 over 2 by 2. But whatever you do to one coefficient, you must do to all of them. So in other words, you have to multiply this entire equation by 2. So now we get 2 C4H10 reacts with 13 O2, right? Because the 2's canceled out, to produce 8 CO2s, right? Because we had 4 to start, times 2 is 8, plus 10 H2O. We had a 5 there originally, times 2, that makes 10. And doing a final check, we have 8 carbons on the left, 8 carbons on the right, 20 hydrogens on the left, 20 hydrogens on the right, 26 oxygens on the left, 26 oxygens on the right. And everything is balanced. All the coefficients are whole numbers, and they're in the simplest ratio possible, a 2 to 13 to 8 to 10. Now I want to ask you a question. If you've ever worked with a flame in the lab or used a gas stove at home, you may have noticed that flames can be different colors. Sometimes blue, sometimes yellow or orange. But which one do you think is hotter? If you said blue, you are absolutely right. And here's why. You see, there are two types of combustion: a complete combustion and an incomplete combustion. A blue flame is the result of a complete combustion, meaning there is a sufficient supply of oxygen. And this allows the fuel to burn efficiently and release maximum energy. But a yellow or orange flame indicates an incomplete combustion, where oxygen is limited. Because the fuel doesn't burn completely, less energy is released and pollutants can form. Let's look at our first example. It says, write and balance the incomplete combustion of methane to produce carbon monoxide and water vapor. So we're going to go ahead and start with methane, right, CH4, reacting with a limited supply of oxygen gas. And that's going to produce CO and H2O, because carbon monoxide is CO. Now, for carbon, we have one on each side, so it's already balanced. But hydrogen, we have 4 on the left and 2 on the right. So if we add a 2 as a coefficient in front of the H2O, now we have 4 hydrogens. Counting the oxygens on the right, we have 1 from the CO and 2 from the H2O. So that makes a total of 3 oxygens. And since oxygen is a diatomic, we can do the same trick as before where we write a fraction. So we can write 3 over 2 in front of the O2. To remove the fraction, we multiply the entire equation by 2 to cancel out the 2's from the 3 over 2. And now we're left with 2CH4 reacts with 3O2 to produce 2 COs and 4 H2Os. This is an incomplete combustion because carbon monoxide is formed. But let's try another example. Write and balance the incomplete combustion of ethane, C2H6, to produce carbon or soot and water vapor. And soot is essentially solid carbon, and you'll see it in places like chimneys, smoky fires, poorly ventilated furnaces, factory exhaust. You get the idea. So starting off by writing the skeleton equation first, we have C2H6 reacting with O2 to produce soot or carbon solid and H2O gas. Balancing the carbons first, we have 2 carbons on the left and only 1 on the right. So by adding a 2 on the right side in front of carbon, we get 2 carbons on both sides. Hydrogen, we have 6 on the left and 2 on the right. So if we add a 3 in front of the H2O, now we have 6 hydrogens on both sides. On the left, we have 2 oxygens, and the right we have 3. So similar to the last problem, if we do a fraction, so in other words, we put 3 over 2 in front of the O2, we can get rid of the fraction by multiplying the whole equation by 2. So that we can get 2 C2H6 and 3 O2 to produce 4 C and 6 H2Os. And again, this is an incomplete combustion, right, where oxygen gas is limited, right? And this time the pollutant formed is soot, also known as solid carbon. Okay, so why in the world does this matter? You see, guys, in the real world, combustion reactions happen constantly. And a complete combustion is ideal because 1, it maximizes energy output, 2, it produces fewer pollutants, and 3, forms only carbon dioxide, water, and energy. And examples include properly adjusted gas stoves, well-tuned car engines that burn fuel efficiently. And unfortunately, incomplete combustions are very common and can be quite dangerous. Some examples include smoky wood fires, so soot, poorly ventilated heaters producing carbon monoxide, engines or furnaces with limited oxygen. And carbon monoxide is especially dangerous because it's colorless, odorless, and very toxic. You see, guys, understanding combustions helps scientists and engineers design technologies that reduce pollution and improve safety. And that's all for today. If you found this video helpful, please don't forget to like and subscribe and check out my community page for practice questions. In the next video, we'll be diving into single replacement reactions, so definitely stay tuned for that. Until then, happy studying!